So, as I said, thank you to attend this talk about the status update of the graphics stack in the Raspberry Pi device. And thanks also to the organizers of the FOSDEM and especially to the people organizing this deploy, which is great. So let me introduce ourselves. My name is Juan, and with me is my colleague Casanova. We work in Galia and the graphics team, and we are working on the Raspberry Pi graphics stack. So what is it talk about? Is basically cover the change that happened in the graphics stack since the release of Raspberry Pi OS Bullseye edition was in November 2021 up to the latest version, which is Bookworm, which was released several months ago in October 2023. So, I mean, this is for people that are not used to with terminology with MISA. We have like 5 devices, Raspberry Pi devices. Well, there are more, but are like variations of those devices. The Raspberry Pi 1, 2, and 3 use the GPU from Broadcom. It's called Video Core 4. And the name of the MISA driver is called BC4. And then for Raspberry Pi 4 and 5, they use the Video Core 6 and 7. And the name of the driver changes, like V3D for the OpenGL-ES. In this case, there are support for the Vulkan driver, which is called V3D-V. So, what things happened? Well, probably the most exciting one is the release of the Raspberry Pi 5. This is an evolution of the GPU from Raspberry Pi 4. It's the same architecture, but with more benefits and higher limits, like it has like a higher clock rate, so it's faster. It supports up to 8 render types. It has better support for subgroups operations, which is interesting for Vulkan. And it does provides a lot of changes in at the institution level parallelism. So it allows to have more compact shaders, which run faster. Drawback is that it has a bit of less registers, so it suffers a bit of more relative pressure. And this support is integrated in the V3D drivers, and it was submitted for review almost the same day the Raspberry Pi 4 was announced, and now it's released in MISA 23.3, and that's in the kernel 6.8, which is required. As I said, this is more or less the evolution of the GPU. So, of the GPU from the Raspberry Pi 4. So nowadays the features are more or less the same in terms of the driver implementation. So it supports the OpenGL-ES 3.1 and Vulkan 1.2, and does support a non-conformant version of OpenGL 3.1. We will see later. This at this moment. So, from the point of view of the drivers in the MISA, in the OpenGL driver, well, one of the important things was that we promote from OpenGL 2.1 to OpenGL 3.1 with some caveats. I'll explain later. I think this is quite important because at the end, the Raspberry Pi is intended to be used as a desktop PC in most cases. So targeting the OpenGL desktop apps is quite interesting. So there are a lot of applications that requires OpenGL 3 point something, and now they can run on the Raspberry Pi. The upgrade from Bullseye to Bookworm allow us to expose 35 new extensions from OpenGL, OpenGL-ES. And as I was saying before, the driver is not fully compliant of 3.1 because there are some missing features in the hardware. Like for instance, this version requires 8 render turrets. This is fixed in Raspberry Pi 5, but not in Raspberry Pi 4. It doesn't support 4. And then the hardware itself does seamless Q map filtering, and the OpenGL spec requires non-seamless. And then some other formats that are not supported. But all in all, probably these are not the most used features. So we support anything else. So from a practical point of view, probably any application that uses OpenGL 3.1 will work in the Raspberry Pi. Then in the Vulkan driver, we moved from Vulkan 1.0 to 1.2. So this is Vulkan 1.0, 1.1, and then 1.2, which meant exposing like 80 new extensions. If you compare both versions of the driver from Bullseye to Bookworm. So there are a lot of new extensions. Some, I mentioned like extension dealing with subgroups, as I said, which is very interesting for Vulkan. Extension dealing with geometry shaders. But I think probably the most important work done was improving the performance. So when Vulkan 1.0 was released, the target was just having a conformance driver. So we didn't spend any time on making it fast. And during this lifetime, we were working a lot on making it more performant, especially in the shader compiler, to reduce the linear analysis and make strategies to make the shader smaller and run faster. The good part is that the shader compiler for the Vulkan driver is actually shared with the OpenGL, so both the OpenGL and Vulkan share the same compiler. So all the improvements in the driver, in the shader compilers, also affects the OpenGL. So basically the improvements are both for Vulkan and from OpenGL driver. Another thing relevant to mention is that now Think, which is the driver that supports OpenGL over Vulkan, work with the V3D driver. So it means that you can use the Think to run OpenGL applications. And then also Roman Sterchenko was working on that the support for Android. So now you can run in Android in Raspberry Pi 4 with the Vulkan driver. And now my colleague will continue with the work done in the kernel.
Okay, Sam. Well, continuing with our work on Vulkan, on the Raspberry Pi, we need to implement several features that were not available in the hardware. In this case, we need to create what we call CPU jobs, that is part of the behavior that is not available in the hardware support for the GPU. So we implemented that in the Vulkan driver in the user space. But that implied that was affecting mainly to some queries about performance counters, timestamp queries, and compute shaded indirect dispatch. So this caused issues because when we were submitting the different command buffers to the GPU, we need to start the driver of the GPU submissions, do the work in the user space, and then continue after having the result. So one of the improvements that we have just recently landed in upstream in the kernel was these kernel CPU jobs. So we move this operation that are already known to the kernel space. So when we are creating in the Mesa driver the submission, we just say the kernel is going to handle that, so we don't stop the submission of GPU jobs. That was a quite interesting improvement in terms of performance, because before this there were a lot of stalls, the submission. Another feature that was quite interesting for the users at the end was to know if they were using really the GPU when they're running the different applications. It would happen for a lot of developers that say, I don't know if this is really working with the GPU. So we implemented GPU stats. We expose these users stats per process using the standard way doing in DRM. And we also expose a global stats. So this way some application just, if you want to know the global status of the GPU, just check that the value of the percentage of usage. Because in other case, you need to go to every process, check each process which amount of GPU has been using, and do the complete sum up. So because of using the standard interfaces, we can run applications like GPU top. That is very nice because it works for several drivers. And at the end, for the global stats, as there is no a common defined interface to expose that, we are currently using a SysFS. So the hardware lacks some some features to provide the stats as other drivers are using, in the case, for example, in Intel. So we go to a simpler approach, that is just we put in the DRM scheduler, when we submit a job to the GPU, we just get the time stub, and the job ends, we get the finished time. As we are only processing one job on each queue, we have the information about how much the GPU was used. So we can show here, for example, well, it's on the top right of there is a graph with a widget that the users can check if the GPU usage. And in the task manager, we already have the information about the GPU users. For example, in this screen, the main user of the GPU is Chromium, and the second one is the compositor. In our case, it's Wayfire, because it's compositing all the different windows and surface that we already have there available. So, well, those are the highlights of the modifications from the kernel. And one of the main important changes that we did from Bullseye to Vulkan Raspberry Pi OS was the change from the default desktop. Previously, in Bullseye, we were running, for the Raspberry Pi 4 devices, Matter with Xserver, and it was working OK. And for the previous generation hardware, Raspberry Pi 1, 2, and 3, we were running the previous desktop we had. That it was OpenBOS with Xserver. Matter was too heavy for this generation of hardware. And when we have this release of Bookworm, now all the Raspberry Pis that install the public image, they get a Wayland desktop using Wayfire. That was good. And for Raspberry Pi 5, it was just released, that is the default one. For previous generation, we still maintain the OpenBox and Xserver, but I want to comment on this. Now, this the last part of the talk. So, well, Wayfire is using OpenGL for doing the composition. It's based on WL roots backend. We use the OpenGL, but it's quite tight for OpenGL. So all the plugins are implemented there using the OpenGL API. One of the most important things we did in this transition from Bullseye to Bookworm was that the user experience don't change a lot. So as we can see, the Simon Long from the Raspberry Pi has done a lot of effort here. So it's difficult, if you don't see the change of the background, to figure out what are the difference between the previous version and the new one. That is Bullseye, and this is Bookworm running. So all has been rewritten, the panel and the theme, because there are different compositors. And well, now we go to the desktop on the previous generations of hardware. Well, we are still using the Xserver with OpenBox. This is the file we have. This has been the same way since Bullseye. We didn't transition to Matter. The main cause of still using this is that we need to use software composition. We use the CPU to render the desktop, because the hardware limitations is supposed to have a memory limit that is 256 megabytes by default. The problem is that we don't have control when the GPU memory that is using the CMA, continuous memory allocator, runs out. So at the moment, we launch a new Chromium browser tab that uses CMA memory. If we run out of the memory, next application that can do the following allocation could be the Xserver, and it can crash, or the compositor. So the solution, it has been there during all the time, is on these devices, all we are using is CPU software composition. So Glamour has been off all the time, and there is no hardware support. You can run a full screen application. All has been, you can enable it, but it's not the default. You can enable Glamour and you get hardware acceleration. But you are exposed to crashing your desktop at any moment. And there are a lot of hungry applications, like the browser, that can kill you if you open 6 tabs. You completely frozen the desktop. So during the previous development cycle on both sides, we wanted to make the possibility of enabling the hardware accelerated application. So if you want to launch your GLXGRs, that GLXGRs is not using LLVM pipe and is using the driver for the hardware. So we managed to do that. We enabled the hardware acceleration on the for applications while we were still doing software composition for the rest of the desktop. So in case you run out of memory, what is going to crash is just the application. You are not exposed to the X server crashing or Matter crashing or whatever application, because they are not prepared for when you do a memory allocation, it fails. We assume that all the time it has been working. This was implemented modifying the model setting driver in the index server. We implemented the support for DRI3 in this case, but without the need of using Glamour. How it is currently written is just Glamour enables the DRI3. So on Raspberry devices, we can use DRI3, even we don't have doing the OpenGL, doing the composition of the general browser. There is a merge request for text server, but there is now too much interest in integrating that. But we understand because X server development is start at the end. But we have been using that downstream for almost a year. It was a huge improvement for the users. And with these changes, we avoid the problem of the GPU memory exhaustion. So, well, when we were about to release Bookworm, the idea is, well, we are transitioning to Wayfire as desktop compositor. What can we do for the older generation devices? Well, we need to rethink again how we solve the previous problems with the X server, now with Wayfire. So we need do the software rendering composition using the CPU, and we would like to allow again hardware accelerated application. Well, the problem for using Wayfire to do the software composition is that Wayfire is quite tight to use OpenGL. It's using WA roots backend, and it's using several in parts of the code, mainly in the plugins, doing the different effects. We are doing calls to OpenGL API, and we don't want to do that. So the first thing is WA roots already has a Pixman backend that is working, so you can just transition, and the parts of WA root that are using Wayfire just do small changes to use the Pixman backend, and it works. The next part is we needed to re-implement all the parts that were tied to OpenGL in the different plugins that we're going to use in the distribution. There are some that are quite complex that we didn't need it, so we didn't implement the change, to use the Pixman rendering logic. So this way we managed to get all the rendering done by Wayfire to be done using CPU rendering. And well, the problem is that if you do that and you start doing blending operations, in our architecture, they become really slow. Because reading from the event buffer when they're doing the blending, assuming that we have synchronous memory, that all the changes are flashed at the moment, is terribly bad. So we experimented with enabling for the buffers we use for doing the dump buffers to use non-coherent memory. That makes that if you write on the CPU and then you put it on the display, maybe there is not coherency. So you start needing to flash in some places. You need to handle that. Some things happen funny because in 32 bits ARM is different to 64 bits. So things that work in one place, in 32 bits you can just, I'm going to flash the memory before put it on the display, and it works. In 62 bits it doesn't work. At the end, the flash is not doing it. In our architecture, doing nothing. So we need to handle the synchronization, but in the compositor to do that work. But well, the difference is of that change is that everything runs fast enough. But well, the problem is that when you enable non-coherent buffers, you only want to do that for the compositor, but not the rest of the application. So that's complex because some applications don't want coherent buffers, and we were dealing with that. Maybe enabling it with a parameter, creating a new IOCTL for getting non-coherent buffers, or well. So well, and for the other part, that was quite fast, as we already know, the part about getting hardware-accelerated application, because we already have the knowledge of doing this on the server, so at the end, we need to handle in WL routes to pass in the PISBAN backend, to pass modifiers with the DMA buffers, and it was already working. No? So I'm going to show this is the current work in progress we have with this work. This is a Raspberry Pi 3 running the desktop. It's using the non-coherent buffers. In other cases, you will see how frames were moving. The performance is quite good. Some of the more complex things, that the most expensive, is the shadow calculation. You cannot imagine doing this in the CPU. Every time you scale a window, is complex. We are seeing that this GLXGR is using the hardware acceleration, and it's not the best thing that we can do because there are possibilities of having another different plane to show that there is on display, but we are bleeding this to by the compositor. And well, we have enough time, I think. So we are going to see several plugins working. So as a conclusion, we are on the point of maybe thinking about putting this for the users, but it's still not ready. There is work always in the... One of the things that Raspberry Pi devices has is try to maintain all the generation of hardware, because you can run the last Raspberry Pi OS with the Raspberry Pi 1 and it will work. We have already tested it with the Raspberry Pi 1 that has slower memory. Juan was doing that test and was good enough. No? It's comparable with the results we are having with the X server. And well, we are seeing Chromium running that is using hardware acceleration. And well, the good thing is that as we are not spending memory of the CPU, we can run more applications. But you can crash Chromium, just open, I think it's 8 tabs. You will crash Chromium, but probably in some cases, only one window. This is the Zoom working. This is all software composition. And I think that's all from us. You can see, we already implemented, this is the switcher that has Wayfire by default, re-implemented with Pisman, and we tried to do a more simpler option, but this one was already working fine at the end. So we maintain the most complex part is doing the transparency and using the alpha channels in software. So, question, I think we are on time.
What Vulkan features do need the CPU to actually get in and do the job? And are they used a lot? Do the applications need them? Will that impact performance?
Well, our colleague María has a blog post explaining this, and they are really... the question is, which features in particular are needed to be done in the CPU and cannot be done in the GPU? I think I already commented. There are some things related to performance counters, mainly if you want, when you are running the CPU commands, to reset the counters. This needs to be done in the GPU. No? You need to write in a register in particular. The other one is related to getting the timestamp, because there is no support to getting the timestamp from the GPU. And the other one is indirect compute shader dispatch. Is that when you are sending several instances of a compute shader, in this case you need to send in the CPU one by one, because there is no support in GPU. So you just submit the buffer to the kernel, and the kernel is going to handle that. Not in the other case, you were in the user space, you send one, wait, and you're going to send one by one. So, well, time's up. So thank you very much for your attendance.